Thank you all for joining us. Thank you for your patience as we wanted to make sure everybody got in that could and could get a seat. We are victims of our own success, and it's no surprise. I'm so excited to welcome you here. My name is Jim Davenport. I'm an astronomer and a professor here at the University of Washington, and it is my great honor to be the new director of the Dirac Institute, which is hosting this event tonight. If you don't know the Dirac Institute, make sure I hit the right button. If you don't know the Dirac Institute, we are a research group within the Department of Astronomy who is at the intersection of computer science and algorithms and big data and classical astrophysics. And that is the heart of what makes this observatory and this mission and this amazing science that you're going to hear about today possible. Tonight we're going to celebrate an incredible milestone, the first images from this beautiful telescope. We're going to celebrate 20 years of effort here at the University of Washington. We're going to share some of the stories and some of the team that have brought you this amazing data and this amazing telescope and this vision. Monday, we saw the very first images from this telescope, and it was, even for me, even a seasoned professional, an awe-inspiring, just grinning ear to ear all Monday morning, watching these telescope images come out, watching the community celebrate, and it fills me with such joy to have you all here today. Thank you for being here. Now, we wouldn't be here without an amazing team, and so let me just spend a minute recognizing the people who have made this possible. The Dirac Institute, like much of astronomy, is funded through an amazing dynamic mix of both private and public funds. We have partners like the Simone family who have given to both the telescope and also to our institute. We have major organizations, major research foundations, NASA, the NSF. We get to partner with everybody because everybody loves astronomy. And so it's with heartfelt thanks that we recognize these individuals and these organizations that have allowed us to be here and that have supported us now for 20 years and for many more to come, I hope. Rubin is a transformation. We are building both technology and tools like AI and machine learning tools that are going to revolutionize our understanding of the cosmos. And we are going to discover things that we don't expect. This is going to be this timeless astronomy practice of looking up at the sky and watching carefully and listening to the stories that it has to tell us. And the most important story it has to tell us is the story of the people. And so I want to just close my remarks here by recognizing the Dirac Institute itself, the people who have become my friends and my colleagues over this last 8 years, the last 20 years, the students, the staff, the faculty, the researchers who have put their heart and soul into this telescope and into this data. And I cannot wait for you to meet a few of them, and I can't wait to share with you these stories. You're going to hear from 3 wonderful speakers. They're hidden amongst these fun photos here. Just as a note, we are recording this event, so we are with UW TV. There will also be a chance at the end to ask a few questions. We're going to do just a little Q&A at the end. We'll run a mic around. So as you are engaging in that timeless practice of watching and listening and thinking and wondering, think about your questions. And we would love to talk to any of you, about what amazing things we're seeing in the universe. So please join us now for an amazing journey through the cosmos. And it is my joy to introduce the provost and the the executive vice president for academic affairs at the University of Washington, Provost Dr. Tricia Serio, who's going to welcome us. Thank you.
Thanks so much, Jim, and thank you all for joining us here tonight. I was just saying to Jim earlier today, there are few things that could bring together people from varied interests like this in wonder, and that's the power of science and the impact it can have on us together. More than 20 years ago, the University of Washington faculty recognized that dreaming big about the Rubin's capabilities in leading the scientific charge could shape our knowledge of the solar system and propel innovation in data science, not only in astrophysics, but across disciplines. But big dreams, especially bold dreams like this one, daring dreams, don't just happen. To become reality, they need engagement from academic, government, and industry partners, and the expertise of faculty, the contributions of researchers, postdocs, students, and the ongoing support of generous donors, such as Lisa and Charles Simoni, and Janet and Lloyd Frink, who share the vision and the commitment to what's possible. In 2003, the University of Washington partnered with the University of Arizona, the Research Corporation, and the National Optical Astronomy Observatory to create the LSST Corporation. And as everyone here knows, leading a scientific charge, especially on this scale, not only requires vision, but expertise, and also time and patience, a lot of patience, right? We heard this started 20 years ago. This makes this celebration tonight even more important. I personally first learned about this project when I was a faculty member at the University of Arizona, and I can't tell you how thrilled I am to be here today, all these years later, to see the first images. Andy Connolly just asked me a minute ago if I was going to stay for the whole thing, and I was like, there's no way you're getting me to leave. I'm really excited. So today, this new 10-year movie of the sky marks a new era in astronomy and astrophysics, and we all get to share in that today, where software and algorithms are as important as the hardware, and an era in which AI and machine learning will help us to see the 1 in a billion objects that we have only dreamt about. Rubin data, as we'll learn today, will deepen our understanding of dark energy and dark matter, trace the history of our solar system, detect asteroids and new worlds, and uncover other cosmic phenomena. This is the most open astronomy project ever. Provides public data in real time every night. What an accomplishment, and thanks to software written here right at the University of Washington. So through interdisciplinary research and education all across campus and around the world, more dreams will be realized and discoveries made. Tonight is just the beginning. And it's all going to be based on the data that come out of the Rubin Observatory. The UW's DIRAC will be key leaders in this project, as they have been all along, writing algorithms that will enable us and anyone who wants to use these data. A project that could only be realized with our own constellation of stars that connect innovation in software and computing to astronomy and astrophysics, with supporters and donors who believe in the power of what's possible. We often talk about the impact that the University of Washington is having here in our own state and around the world. And this project will now take us far out into space and give us and many others information about the very origins of the universe and set the stage for future discoveries that we can't even articulate today. And now, I'd like to introduce Professor Željko Ivičić, who's been associated with the Rubin Observatory since its inception. Since 2022, he's been the director of the Rubin Observatory Construction Project, and he joined the UW as project scientist in 2004. He's been leading the efforts that we will hear about and see all along the way. And scientifically, his own expertise is in survey astronomy in a variety of fields, ranging from solar system science to studies of the structure of the Milky Way and cosmology. Please join me in welcoming.
Thank you. Thank you, Professor. Thank you all for coming tonight to share in celebration of first images, first data from Rubin Observatory. Rubin Observatory is the greatest astronomical discovery machine ever made, and we are celebrating the start of its data taking. But we are not only celebrating the start of Rubin Observatory, we are also celebrating a major role that the University of Washington has been playing and will continue to play in Rubin Observatory and in science with Legacy Survey of Space and Time, LSST. UW was one of 4 founding institutions of LSST Corporation, an organization that started the whole project. That organization and the project itself later grew to over 40 institutions. But UW is still playing a major role. Indeed, once we go into operations this fall, the observatory will be managed by 2 national labs, by National Astronomical Observatory in Arizona called NOIR Lab, and by SLAC Laboratory in California, DOE-funded SLAC Laboratory. There are only 2 universities that will be playing a major role in operations now that we built the observatory, and they are Princeton University and the University of Washington. So we are continuing our major role. Thank you. Go UW. So how did that happen? It happened because of 2 decades of strategic visionary decisions by the Department of Astronomy, by the College of Arts and Sciences, and UW leadership, like Provost and President. And I want to emphasize 2 decades of hard and exciting work by our team that we are also celebrating tonight. They deserve to be celebrated because they built the thing. How did that happen? So in late 90s, early 2000s, the Department of Astronomy was exploring strategic directions they could take. They wanted champagne level on a beer budget. It's always hard to get funding. At that time, the department already had great success with the pioneering survey of the sky called Sloan Digital Sky Survey, as well as with Astrophysical Research Consortium 3.5-meter telescope project. So the department decided to pursue survey astronomy as a growing field. They recognized that the rapid development of computer technology, of computing technology, of telescope technology, of sensors will enable unprecedented data-taking capabilities in near future, and decided to bet on this project. They participated in that LSST Corporation. They founded with 3 institutions from Arizona. And then, because of support from university leadership, started hiring faculty. They hired first me in 2004 when I was young and full of energy. I'm now only full of energy. And then we continued with Andy and Mario and Eric Bellum, and we built an amazing group that you will hear more about later in these 3 presentations tonight. So I want you to remember that UW is a key institution in Rubin universe, in part because, as Provost already mentioned, we had an excellent support from beyond university. And the most impressive one is a major gift by the Simoni family and Bill Gates that allowed us to procure primary tertiary mirror for the telescope that is now named Simoni Survey Telescope after them. So what is Rubin about? What we want to do is exceedingly simple. We want to scan the sky over and over for 10 years. And we want to do that with a digital camera that is the largest ever constructed. And so that will allow us to scan the sky fast and very sensitive levels. And that will allow us to get a huge sample of objects, unprecedentedly large sample of 40 billion objects. This will be the first time in history of astronomy that an astronomical catalog will include more celestial objects than there are living people on Earth. So you could literally name a star and a galaxy after every person on Earth, including you. And what's better is that we will, over those 10 years, image each part of the sky about 800 times. So there will be frames in a movie. You can compare them to see is anything changing in the night sky? And although most people think that the sky is static, indeed, the sky is very dynamic, and my colleagues will make a point of that in their presentations. Rubin Observatory is sited in Chile. Chile is the capital country of astronomy in the world. They have amazing local observing conditions. So over 60% of astronomy power measured through area of your mirror. This is what collects photons. Over 60% is in the country of Chile, and they are providing huge support to both American and European observatories there. There is even a government agency that supports astronomers. The project is funded federally by National Science Foundation and Department of Energy. But as I said, in the early days of the project, the support by private gifts was substantial and critical for success. Why is it called Vera Rubin? Originally, we named it Large Synoptic Survey Telescope. But then, after 2 Congress people proposed to change the name, it was adopted in 2021. Vera Rubin was an amazing person and an amazing scientist. She's credited with providing first convincing evidence about dark matter. Some people propose that there is something fishy there with gravitational force in the universe, but it was based on much weaker thermodynamical arguments. Vera Rubin and her collaborators measured the motion of stars and developed a very simple argument based on mechanics, so no hidden thermodynamical complications. Very simple argument that demonstrated that stars are moving as if there was some hidden source of gravitational force or potential that we do not see. We know stars produce gravity. We can calculate how much that we should see. She realized that actually what motions of stars show is that something's missing there. There is something that doesn't emit light, hence dark, but it produces gravitational force, hence dark matter. But she was also a great advocate for participation of women in astronomy and science in general. When she worked, especially when she was a young student, women were not encouraged to come to observatories and often forbidden to come to observatories. And she was a trailblazer who fought for her right to go to the largest national observatories to observe. And I'm proud to say that among all the large astronomy departments in the world, the University of Washington Astronomy Department has the largest fraction of female professors, and we essentially have a gender balance. Thank you. Thank you. And that result is in part due to the fight that Vera Rubin did throughout her life. So what do we want to do? In short, we want to capture the cosmos. That is enabled by 3 technological breakthroughs. By the largest camera in the world. So that camera was enabled by rapid development of CCD sensors for capturing photons and turning them into electrons. It was enabled by our ability to build a very large telescope, 8.4-meter mirror, that can be very agile. We will be making images with 30-second exposures. And when you go from one point on the sky to the next point, that time has to be small compared to 30 seconds, or you would be just wasting your time slewing. And the problem was that classical 8-meter telescope takes minutes, and we wanted it to be 5 seconds. And so that was produced with this telescope. I'll show you a little video. And finally, you also need ability to see faint objects, to make movies, and that together will give you the greatest astronomical movie of all time. If, after 10 years of LSST, you decide that you want to see all the data with your eyes, and you want to watch what happened on the sky, it would take you 11 months of uninterrupted viewing. Huge data set. Raw images will be 60 petabytes, and the full data set with metadata and auxiliary information will be 500 petabytes, 500,000 terabytes. Obviously, we'll have to use computers to process it. So the concept is very simple. It will be a powerful observatory, and what we want to do is to relentlessly scan the sky and to enable science that is not possible today. And I'll talk a little bit more about science in a few slides. The observatory is sited in Chile. It is AURA property, where AURA stands for Association of Universities for Research in Astronomy. That includes about 50 US universities with few international places, and that UW is part of. They built major astronomical observatories in Chile on behalf of the US government. And so now I will show you how we built the observatory the first 10 years. We had to level the hill, and then we started building it. There was a lot of surprises, like thinking it's hard stone, hard rock, and then we found clay. Had to bring a lot of concrete to make it stable. The building was built by a Chilean company. The dome was built by an Italian company. We were thinking we are getting close to being done, and then COVID kicked in, and that added 2 extra years. There is also music with this video that Andy said it's horrible, and he censored it. And this is when we put the final piece of telescope with the largest crane in Chile. And so now I will demonstrate to you quickly how fast the telescope is. All big telescopes take minutes to turn around. And this 300-ton monster can do it from one side to the other, 180 degrees, in about 20, 30 seconds. It is essentially a battery-operated telescope because when it moves, it draws 1 megawatt of power. But power lines that come to the summit, they don't have capacity of 1 megawatt. So we have giant capacitors that when you have to move, you draw energy from capacitors, and then when you brake, you return the energy. It's a technological marvel. And so let me now quickly go through science motivation for this project before I show you first data from the observatory. There were 4 science cases that we used to justify 20 years ago building of this observatory. They are not the only science that would be done with the data, but we use these 4 themes to size the system. For example, how large mirror do we need? How many pixels in the camera we need? What kind of software we need, etc. And so they include dark matter and dark energy. That is interest from the Department of Energy. And then Milky Way structure, solar system census, and then because we will be getting time domain information, then the changing sky is the 4th pillar of LSST science. So we predict that we will be detecting up to about 10 million changes in the sky per night. Later you will see, you will learn from Mario how our team here has developed the best software framework in the world for subtracting images and discovering the differences between the two. And we will find up to 10 million such differences. We will release them within 60 seconds to everyone in the world to filter for objects that they are scientifically interested in and deploy their own facilities that will get more data, similar data to Rubin, or completely different data, spectroscopy, different wavelengths, etc. In the context of solar system, we will be a game changer. There are about 1 million asteroids known today. In the first few years, Rubin will detect LSST data, will enable discovery of another about 5 million in first few years. So in first few years, we will outdo 200 years of asteroid searches since the discovery of first asteroid by a factor of 5. Amazing. And that's because technology is developing so rapidly. You will learn more from Mario about our first discoveries of asteroids. We also, because we are scientifically motivated to find asteroids, the way we observe and the way we process the data enables discovery not only of asteroids that we are interested in scientifically, but also of those that are on near-Earth objects and on near-Earth orbits, and potentially can be hazardous objects, can collide with Earth. And we will get the best ever data set in that context too. Because we can look at things that change, we will be discovering supernovae in automated fashion, about 3 million supernovae in 10 years, which is mind-boggling compared to what we have today. And supernovae are gold in cosmology. They are easy to get distance for, relatively easy. And once you know their distance, you can do cosmology. We will also find many variable stars, indeed few 100 million variable stars. And today we know only of maybe few million that are cataloged. We will do unprecedented mapping of Milky Way structure. Today we can go to about 1/10, maybe 2/10 of distance to the edge of galaxy. With LSST, we'll explore the very edge of our own galaxy, the Milky Way. We will detect close to 20 billion stars in the Milky Way. An unprecedented sample. The largest data set today is under 2 billion. And in the context of dark matter and dark energy, the shortest way to say what we will do is we will test if Einstein was wrong. What's that about? So we know that the universe is accelerating. And there are two ways to explain that. It is totally unexpected. If there is only gravity on these scales, the expansion of the universe should be decelerating, slowing down. But it's speeding up. That was discovered about 2 decades ago, and those guys got Nobel Prize for that. So one way to explain it is to say, well, there is some mysterious new component of the universe that we don't see, but it gives that energy for acceleration. It's called dark energy. We don't know much about it. The other way to explain it is to say, well, wait a minute. When you started deriving your conclusions, you assumed that we understand gravity, that Einstein's theory of relativity is correct. But what if you need to modify it? Then you don't need dark energy. And indeed, theorists, being theorists, they found like hundreds of ways to modify it. And they all explain what we see on the sky. But we don't know which of these possibilities is correct or less wrong than the others. Today, our data are not good enough to answer this question. In 5 to 10 years, we will answer this question with LSST data. There are a number of ways we get constraints on what's going on. One is gravitational lensing. These are tiny distortions in the shapes of galaxies where at the level of 1 or 2%, because mass warps space, and effectively it acts like a lens. When you have ordinary lens in your glasses, it changes the shape. So to do that effectively for cosmology with precision of few percent, you need billions of galaxies. And that is why we need to have a big telescope. That is why we need to be very sensitive to detect faint galaxies to get to the count of 20 billion galaxies. You can't do it with small telescope. The other one is to look at the distribution of galaxy clustering that gives you a handle on the growth of structure in the universe and breaks some of those degeneracies that I implied when I said there are many ways theorists could do it, but they don't know which way. And supernovae, as I already mentioned, are standard candles. We know how to get their distance, and then we can map in time expansion of the universe very, very precisely and measure acceleration. And perhaps the most exciting part of our science is those results that we will get that we didn't think of. Every single survey before LSST that was revolutionary for its own time, that was better than what we had before, every single survey, like for example SDSS, discovered new things that nobody thought of. And we anticipate we will get many unknown discoveries, unknown unknowns with LSST. It will be a huge data set. It will be 500 petabytes. It will bring us completely new ways of doing astronomy. You can't do it anymore with a bunch of grad students, like you go one night to telescope. This is different ballpark. We need to teach our students to be as good in astronomy as computer science students, because this is the tool that we are using today to look at our data. Our eyes are not good anymore. Our brains are falling behind, and you will learn more from Andy how he's planning to count that in his case. So another great aspect of our observatory that also Provost already hinted at is that the data will be open to everyone. Everyone in the United States, in Chile, immediately gets access to data and data products. And after 2 years of proprietary period, literally the whole world will get to everything we have. But even better, those alerts that I told you about, they come out in 60 seconds to everyone in the world. No limitations. And our excellent tools for doing education and public outreach will also be public to everyone in the world. So we are truly in open source project that will reach to millions of people with new astronomical discoveries. So let's now see some of the data that we collected. It all started on April 15th, not so long ago. First photon, we thought it would take us whole night. We did one image, it was out of focus. We fixed it, got second image, 30 seconds. It was almost perfect, and the third image was literally perfect, and we were staring, and what happened? Where is the champagne? We were all so happy, and we are still happy. We have been dreaming about the night for 2 decades. And it finally arrived. And not only that we quickly obtained beautiful data, but also we continued doing so, and every new image was better, better, and better, and the observatory is performing beyond all our expectations. This is the image that we released on Friday. It's beautiful, it's color image, it's very sensitive. But fun fact about this image is that it is only a tiny portion of the actual image we took. Our field of view is huge. This image is 50 times smaller than our full image. Why is that? Why am I wasting your time by not showing you the full image? What about this teeny tiny image? So let me explain. So this is our big, beautiful camera. And it has 3,200 megapixels. And the problem with so many pixels is that your eyes, my eyes, human eyes, they are not good enough to see that image. Your eyes do not have a resolution to resolve 3,200 megapixels. That is why we could only show you this tiny image in the bottom right, and now in the upper right you can see its size relative to the full field of view. If we wanted to display image from the full field of view, we would need 400 high-definition television sets. Modern TV is kind of adjusted to be a resolution what human eyes can do. So we would need 2 TVs per sensor, or about 400 TVs. This is a basketball court full of TV sets. So if you wanted to see one image from Rubin, you could walk by basketball court and look at those 400 TVs. That's one way to do it. It's not very practical. The other way to do it is to use a tool, a new web display tool that our team developed that would allow you to zoom in, zoom out, change your mind, go to different objects, zoom in, look at it, enjoy it, zoom out, go to another object, and that is what I'm going to show you in the next video. The video is overwhelming, trigger warning. Your eyes may open, or your mouths may open. So first time we'll go through it, I'll keep my mouth shut, but then I'll go again, and then I'll say a few words as we enjoy it. So let's do it once more, and I'll interrupt a few times and try to explain what we are looking at. So we start from a bunch of spiral galaxies. We zoom out. Something happened with the sound. I don't know what. From my position, there is some echo. I don't know what's going on. So you can notice that there are many different colors. Let me Are you having trouble with sound? No? Something's happening with here, some destructive interference or something. Okay, let me jump to... So this is beautiful collage of different objects. You can see these big objects. They are very distant galaxies, about 50 million light years from us. The blue one in the bottom right is spiral galaxy, and it's blue because it's producing young stars, baby stars, vigorously. The other galaxies, the big ones, the reddish, they are much further away, and they also don't have young stars. They only have older stars that are yellowish and reddish. And then you can see many tiny specks of light in the background. These are mostly stars in our own galaxy. And they are 1,000 to 10,000 times closer to us than these large galaxies. But they're individual stars, while galaxies have billions and billions of stars. Colors are very important here. From colors, you can tell distance to objects. And that's important for galaxies because that's how we do cosmology. It's also important for stars because that's how we study the structure of our own galaxy, the Milky Way. So let's zoom out a little bit more. There is another beautiful region with two spiral galaxies. They were photobombed by asteroids, but you don't see asteroids in this image because we remove them using our software that can recognize them and remove them. But if you're interested in asteroids, then you look at those guys that were removed, and that's what my colleague Mario will be telling you in a few minutes. Here, too, you can see these amazing different shapes. You can see merging galaxies in the middle top. These galaxies have unusual shapes. That's because they are distorting each other with tidal forces from their shapes that they had, like these other galaxies. They came too close to each other, and they're now interacting gravitationally. So here at the end, you can see the full extent of that region on the sky. It's about as large as 2 fields of view of LSST of Rubin, or 20, about the whole image is 25 square degrees on the sky. And you can see in this animation how we image the sky. And that, again, is about 100 times faster than any other comparable large telescope. We will do LSST in 10 years if we had to use another telescope that exists, like Gemini South or North, the public US telescopes. We would take 1,000 years to deliver LSST. So we had to build a new observatory, new telescope, new camera to make these scientific goals possible in a reasonable amount of time, 10 years, like what takes grad students to finish or something. Just kidding. So the strength of Rubin, of LSST, will be in this fast scanning of the sky. It will be in these huge samples of objects, 20 billion galaxies and a similar number of stars. It will be in time domain, in studying time variation of sky, things that move on the sky, things that change brightness, all with these huge samples. But as we look at the sky, we look at everything. And so occasionally, we also look at some beautiful objects, nearby beautiful objects. And this is not primary goal of our project, but this is the example of extra science we will be doing with LSST. So I will show you this in a moment. Meanwhile, if you liked the previous video, if you liked going around, zooming in, zooming out, looking at, there are about 10 million galaxies in that image. You can take this link. It's an easy-to-use app. And then when you go home tonight, then you can spend next few hours just going around this image. Turn the lights off in your room, and then look at your screen, and it will be fantastic. We did it, and it's great. So now we'll go to a couple of more beautiful objects, and then we will continue with next speaker. So here again, image is large, you cannot see all the detail. So first I will just show you static image. That image is very large. It's as large as field of view of Rubin, about 10 square degrees. It shows two nebulae. The one in the top right is called the Trifid Nebula, and the one in the middle is called the Lagoon Nebula. Nebulae are giant clouds of gas and dust. And often they collapse, and when that cloud collapses, then density and temperature in the center go up. And once you go above some threshold in density and temperature, you effectively have a new star. A baby star was born. And here in the bottom right, in that whitish circle surrounded by pink, you can see a bunch of stars, a cluster of stars that are baby stars that were born relatively recently in astronomical terms. The beautiful colors are due to excited gas, mostly hydrogen, helium, and oxygen, that is excited by energetic photons that come from stars that were born. That's why we see these beautiful hues. And then in the background, there are hundreds of thousands of stars. You cannot see them right now, again, because your eyes and this screen are too bad. But we will go and zoom in, and then you will see that there are hundreds of thousands of stars in the background. And you can also see these dark spots that look like holes in the sky. They are not holes in the sky. They are stars there too, but they are dark clouds of dust between these stars and us. It is like smoke coming from when you do barbecue and you can't see through the smoke. That's the same effect here. So you block the light from the stars behind that dust cloud, and that's why it looks black and like there is a hole in the sky. So let's now do justice to this image and zoom in, and so that we can see all the detail with our eyes. Awesome. Look at all these background stars, literally hundreds of thousands. This is the size relative to the moon. Astronomers have produced images of this region before, but nobody has ever done it so rapidly like Rubin, only in few nights, and at that great detail level with 3,200 megapixels. Beautiful dust cloud. And so this is why it's exciting to be an astronomer. Thank you so much. We presented this first time on Monday in DC at the US National Academies of Science, and it was covered with so many media. We are still getting numbers that it's just mind-boggling. We had 20,000 TV shows mentioning it, like on the first evening. We already had over 18,000 front pages in newspapers. This is an example. So it's a great success. On behalf of Rubin team, thank you for that. It was a great success. And UW did it! And so now we will look a little bit in more detail and at this data, at what science we got out of it. And we will also try to explain to you great work that was done by our wonderful team here at UW. So we'll have two more presentations. The first one will be by my dear colleague, Mario Juric, also fellow Croatian American. He's an expert for asteroids, and he and his group have turned our astro department into the #1 place in the world to do solar system science with LSST. Please.
All right, thank you, fellow Husky. Željko, there are two people who I think are hugely deserving of praise for making this observatory happen. One person is Tony Tyson, who's at UC Davis, who's a professor who came up with this concept some 30, 35 years ago. The other is Željko, who actually built it. So one huge round of applause for Željko, because he did it. He made this observatory happen. All right, I'm no Željko, but I am slightly younger and a little bit more energetic. Even more energetic, I should have said. And I have to be because I'm going to tell you about the time domain universe. And what do we mean by that? The images that Željko showed you are breathtaking. They're beautiful. They make you feel that you're sitting in this room and looking at the skies that never change. And here's a quote from Lucretius saying, "The sky is the same now as it was before. The stars go on in their eternal course." But is it really? It's not. All of you know about comets. Here's an example of comet Neowise that was up in the skies a couple of years ago during the pandemic, where a lot of us went out and see it. There's an example of something that changes in the sky. If you look further in detail, you see variable stars. Here's a simulation of a star that pulsates. And as it pulsates, as it changes its size and its brightness, and actually its shape, it changes its brightness. So when we look at the sky, at one point this star has a certain brightness, and the other it's different. So things do change. If you move on to the next level, you're going to see even more extreme stars like this. Most stars in the universe have companions. Some stars have companions that are black holes. And some of those black holes are so massive and attract so much matter that they will start sucking the material away from the star, spinning it into a disk, and then throwing it out occasionally in these jets, causing flares that we see down on Earth. So there's more things changing. And then finally, when you get to the larger scales, when you get to scales of galaxies, you're going to see things like this. For fans of Interstellar, this is a supermassive black hole simulation. A huge disk of matter swirls around it. What you see up here is light from the other side of the black hole that's bent over it by gravity that's coming to us. These kinds of black holes, as it eat up huge chunks of matter, sometimes have a little burp, like a baby of sorts. And we see those burps down on Earth as activity in active galaxies, in quasars. So the universe is dynamic, very much so. And Rubin can see this. So now let's take the images that Željko showed you and look at where these changes happen once we zoom in and once we unfold the time dimension. So here's the same image that Željko was showing you, but now we're going to zoom into some stars and look at what they looked like the first time we took this image of the sky, let's say on May 3rd, and then later, a couple of hours later. So this object got 30% brighter. Now let's zoom in on a different place. Here's another star, nice and blue. May 2nd, it looked like this. May 2nd, a couple of minutes later, it got brighter. And now you can do this manually and find a third star, and so on and so on. Or you can write software to do it for you and discover all of them. And when you do that, you discover that these things that seem to be unchanging in the universe actually aren't. They're blinking. So this image, it's not just the size of it. There's a third dimension. As Željko said, this is a time-lapse video of the sky. And that's what we see here as well. Stars changing their brightness, galaxies changing their brightness, other things changing their brightness. The objects that we just seen are called RR Lyrae stars. They are interesting because if we measure how quickly they change their brightness, they pulsate. If we measure how quickly they pulsate, we can actually tell how distant they are. And that allows us to build maps of the Milky Way and of other galaxies. But there's much, much more than just RR Lyrae in this image. As Jelko said, Rubin will reveal 10 million changes like these in the night sky, and that is unprecedented. That's an order of magnitude more than anything we have today. And what's even more unique is that usually you take sometimes days, best case scenario hours to tens of minutes to find out about these changes. With Rubin, we're going to alert the entire astronomical community to these changes within 60 seconds. So that's what this telescope is. It allows us not just to take the unprecedentedly deep images of the entire sky, but it also allows us to tell what's been changing in the sky immediately, rapidly. And none of this would be possible without the Rubin team right here at UW. So what I want to show you over the next couple of slides is exactly what this team did, and you're going to see them later. They're sitting here in the first couple of rows, to make those images that Jelko showed you possible. Everything from the beginning to the very end of that process they were involved in. So let's go to the very beginning. The foundational ideas and design of Rubin are encoded in, I know this is a very exciting slide to show to 500 people in a lecture hall, are encoded in documents. And this here is our constitution. The constitution of Rubin Observatory is called the LSST System Science Requirements Document, and note who the first author is. This goes back to, when was it, 2009? 2004. This document here is called the Data Products Definition Document. This lists everything that we're going to produce and share with the community. And I've just encircled people from University of Washington who have contributed to making it, including Colin Slater, who started here at UW almost 10 years ago as a postdoc, and now is the deputy of this entire system who leads all these universities that Jelko mentioned in making this document a reality. I promise this is the last time I talk about documents. Here's something more interesting. The team at UW also led simulations on how to optimally cover the sky. This here is a simulation of how the telescope moves around and takes images throughout the night. And these decisions that the telescope has to make, because remember, this all has to be automated, have to be made somehow. There's not a person who makes the decision where to go next. The person teaches the computer to take all the data inputs in and makes that decision. And that teaching the computer the algorithms is also something our team did here. Next, we produced first simulations of what Rubin images will look like. This here was built in 2011. We're now almost 15 years later, and we actually have images that look like this. This is tremendously satisfying. It's a group that was led by Andy Connolly in a collaboration and using a software that Andy's very fond of that he can tell you more about. Today, this group develops the software for the active optic system that keeps the telescope in focus. The fact that those images look so well and they're so sharp is due to their work here. And then those variable stars that I've shown you, how do we know that they're there? Because Eric Bellum, Ian Sullivan, and the entire group that they lead told us so. Or actually they didn't, their software told us so. Here's an image of a galaxy. It looks quite ratty because we zoomed in on it a lot. And there's something that has changed in this image relative to when we took this image before. How do we know which one of these objects changed? Well, we can try and go and look, or we can develop software that will subtract these two images, and all that's left is what's changed. And what's changed turned out to be something here that we otherwise wouldn't have seen because it sits right on top of a galaxy. It's a new supernova. To do this is incredibly hard. It looks very easy when you do it in PowerPoint, as everything. But to actually get it done is super hard. That's what the team did here. And then there's no use if we can find these supernovae and we can't tell anyone about it. Remember, I said we want to get the news out in 60 seconds. So we did that as well. Our group here constructed the technologies to take all those 10 million alerts to new things in the sky and then send them throughout the world. These are what are called alert brokers, places that receive data from us that are literally all across the globe. Alerce is in Chile, Ampel is in Germany, Antares is here in the US, Lasser is in Northern Ireland, Fink is in France, and Babamol and Pitbroker are also in the US as well. And we send all of our data to them, and they in turn pass it on to thousands of astronomers throughout the world. But the technologies for all of this have been developed here. It's great to be able to do this, but if the community doesn't know how to do this, doesn't know where to go, doesn't know how to read these data, again, it's no use. So we have what's called a community Rubin science team. It's a team comprised of many, many people across the institutions in the US and beyond that are involved in this project, but they're led by Melissa Graham, who's here somewhere in the audience and at UW. And our solar system expert on that group is Sarah Greenstreet, who is faculty member at NOAR Lab, but actually resides in Seattle and is also an adjunct member here. So solar system is the final thing I want to talk about, because we're also responsible for discovering objects not only that change brightness, but also that change positions, that move. And the only objects that do that, at least quickly enough to be noticeable, are asteroids, comets, planets, and trans-Neptunian objects. And that is what we found in these images as well. So I'm going to click. Once I click my clicker, what you're going to see are the things that Željko said we took big pains to remove from the images so that they look nice. There's a joke internally that asteroid astronomers think of galaxies as vermin of the sky because they're all over the place, and then the galaxy astronomers think of asteroids as vermin of the sky because they keep photobombing the galaxies. But here's that beautiful photobomb that we removed. There's a galaxy, and this, what looks like a star, when you run that movie, you notice that it's moving. That is an asteroid in the solar system. It's not just one. It's not just 9. It's not just 36. You'll see there are thousands. In this one field, here they are. We're here on Earth, but we are orbiting, our planet is orbiting among millions and millions of dots like this. And with only a few images, we found 2,000 of them. Now you're going to see us zoom out. Here's where the Earth is, here's the sun, and now you can see the third dimension here. There are asteroids that are near the Earth, there are those in the main belt, and there are those that are very, very distant away. But yes, we're not just finding dark energy, or we're not just studying dark energy or looking at the most distant galaxies, we're looking at things that are very close to home that we're going to be able to go and visit at some point in the future. So we're extremely proud that this group here at UW has made these discoveries possible. Without them, this would not have happened. All right, now let's just see how well they did it. How well did Rubin do? As I said, in a few nights of observing, we found 2,104 asteroids. So what does that mean? Is that big? Is that small? Before Rubin, the whole world would typically find about 20,000 asteroids per year. So in one night, we found 10% of the typical annual yield in a few nights. This, once we start observing fully, once the test period is over, is going to be an absolute game changer for mapping of the solar system. And I want to just show you how game changing it's going to be. On the next slide, I'm going to show you a simulation of what life would be like if you're an asteroid astronomer over the next couple of years. This is going to be a simulation made by one of our graduate students showing the discoveries as a function of time. So here we're looking at the solar system from the top, and Rubin starts. And what you're seeing here are new discoveries. And look at the numbers down here. This is half a year into the survey. We get to about a year into the survey. We're up to 1.5 million new discoveries. And this goes on and on and on for the next 10 years. And we go up from knowing about 1.5 million objects to almost quadrupling that, to going to 5 or 6 million. That is what this observatory is going to deliver. And our picture of the solar system with this kind of data set is absolutely going to change. So we know of 1.5 million solar system objects today, and it took 225 years to get there. Right, the first object was discovered on New Year's Eve in 1801. And with Rubin, we'll double this in the first year of operations. So, and by the time the survey is done, we'll bring that to a total of about 5 million objects. So why does this matter? You can also go to the beach and say, I can count more sand than anyone else can. But why do we care about this? Here's one reason. Some of these objects get pretty close to Earth. We know of 25,000 of them, and occasionally they get too close to comfort. We would like to know where they are. With Rubin, we're going to go from 25,000 near-Earth objects that are known today to 125,000, five times more after 10 years. So if there's an object with, let's say, our name on it, we hope to find it in time, because we want to avoid things like this. At present, there are only 40% of asteroids known that are capable of causing continent-wide destruction. So here's one. This is an extremely small one. This was the size of a school bus that entered over a city in Russia called Chelyabinsk back in 2013. It sent about 2,000 people to the hospital, broke windows on more than 3,000 buildings. It was not an incredibly pleasant day over there. We would like to know about objects like this, and specifically objects that are even larger than this, far in advance. So Rubin will take that 40% number and essentially double it. If you think about that in terms of risk, right now we don't know where 60% of dangerous objects are. By the time Rubin is done, there'll be only 20% that are unknown. So we'll reduce the risk by a factor of 3. Then we have the science. One of the questions that everybody wants to know is, where is water in the solar system? We think it came with comets. We think it might have come with asteroids as well. What brought it to Earth? How much of it remains in the asteroid belt? With this new sample of objects, that's a kind of question that we'll be able to answer. So finally understanding the water that we drink every day, here's some over here, where did it come from? Then if we go further out in the solar system, we reach this region beyond Neptune called the Kuiper Belt. The most famous member of the Kuiper Belt is Pluto. Pluto used to be a planet. I know, Pluto fans in the audience? Now we call it a dwarf planet. Why do we call it a dwarf planet? Because we found more objects like Pluto. And this is the reason, by the way, if somebody asks you, especially if you're an astronomer, why did you evil astronomers demote Pluto? The answer is, well, if you have kids, would you like them to need to learn names of 8 planets or potentially names of 20 planets? We're making our way up to 20 or so. Rubin should find a few more of these once we are up on the sky and fully running. And then, when you look at how these objects are positioned in the solar system, there's something funny about them. They all seem to be pointing in the same direction. And that's interesting, because in nature, things don't happen by accident. If something is pointing in some ways, it means there's something that's pushing it to point that way. And there's a hypothesis out there that there's a large planet in the universe, in the solar system called Planet 9 that we still don't know about. How large? The size of Neptune, really large. If there's another planet in the solar system, it's more likely than not that we'll find it in Rubin. And not in 10 years, but in the next 3 to 4. And the fun thing is that if it's not there, we'll be able to tell that as well. So one way or another, I hope to get this question mark eliminated from this slide when I give a talk like this in a few years from now. And finally, we're not the only planetary system out there. Our galaxy has billions and billions of stars, each with planets and asteroids. And sometimes they take those planets and asteroids and something happens in that system and they throw them out, and comets as well. And sometimes those comets float over to our solar system and we find them. So far, we've found exactly 2. In the history of astronomy, we've found 2 comets that have come to us from other planetary systems. And that's a wonderful event because all of us want to board a spaceship and go to the nearest planet and go and study it. We can't do that yet, but fortunately the universe has mercifully sent comets to us to study them. We have 2 right now. With Rubin, we're going to be finding between 1 per year and possibly 1 per month. The reason why there's such a huge uncertainty is because we just don't know what's out there. So the next year, we'll know. So this is just a glimpse into what's possible with Rubin. After 20 years of development and construction, the telescope is finally here. And this is, I told you only about the solar system just because we don't have enough time to go through everything that it can do. But I hope I've convinced you this is a discovery engine like we've never seen before. And as Željko said, the challenge right now is how do we discover interesting things in those mountains of data? So it is a discovery engine, but it's only a discovery engine if you can fuel it. So allow me to introduce our next speaker, Professor Andy Connolly, who's the Associate Vice Provost for Data Science and Director of eScience, who keeps thinking about these things. How do we take mountains of data and then turn them into actual knowledge?
No, I think I'm good. Thank you, Mario. I really should let you know that I'm not Croatian American. I wanted to fail the test. I am old, but I'm not as old as Željko. So I just wanted to set all of those things straight. I think we can all agree that the Rubin Observatory is an incredible machine. It's 350 tons of glass and steel that can move across anywhere on the sky within 15 seconds. The data that Rubin is going to collect, the information that it's going to collect is just breathtaking. It's going to really fundamentally change our understanding of the universe, both in terms of how our universe came into being, how our universe and structure formed and evolved over the next 13.6 billion years. But what's really remarkable, and equally remarkable, is if at the end of this event you just go outside and you look up at a quiet space and you look up at the sky, and as your eyes are adjusting to the light or to the dark, if you just put your palm face up to the sky, then every 30 seconds or so, light, a photon from a galaxy billions of light years away will graze the surface of your hand. And with hundreds of billions of galaxies, we are continuously bathed in this light of a distant universe. In fact, the light of a universe that stretches back to just a short time after the first signatures of the Big Bang. With telescopes like Rubin, and with telescopes at the scale and size of Rubin, we can capture that light. Not just to show that there's asteroids or stars or galaxies that are there, but to measure their sizes, to measure their shapes, to measure their brightness, to see how that brightness changes as a function of time, to see, as Mario said, if those objects move. If you wanted to do this with your own eyes, if you wanted to see what Rubin sees, then you would have to have eyes that are as big as 2 London double-decker buses. And try imagine moving those around to see any part on the sky. With Rubin, we can observe a single star as it explodes, as it dies, as it goes through a supernova, exploding and then brightening and then slowly fading from view. But with Rubin, we can do this at an incredible scale, detecting 1,000 supernovae per night. So we don't just see that there are supernovae there. We can learn from them. We can learn how stars are born, how they die, how they evolve and live over the millions and billions of years of their lifespan. And as I think about what we can see, there's really two things that strike me as I think about the science that we're going to do and the discoveries that we're going to make over the next 10 years. One is really a sense of awe. Right? It's a feeling, and in academia today, we don't really get to say that very often, but it's a feeling that is a remarkably privileged time to be alive, to be able to observe the universe with this level of precision and this level of detail. And the second thing that really strikes me is a little bit of terror. What the hell are we going to do with all of these data, right? With millions of galaxies in every image, with tens of billions of stars and galaxies being detected by Rubin over 10 years, with quadrillions of photons that are being captured by this telescope and camera, how do we make sense of it? How do we determine which of those thousands of events that we're going to see every 30 seconds, which ones are interesting? Which of the galaxies should I spend a little bit more detail on? Which one of the objects out there might reveal something about dark energy or dark matter? And this is an incredible challenge that we face. How do we manage this flow, this fire hose of data that's driving towards us that just started less than a month ago? And the funny thing is, we all face exactly the same problem that we face with Rubin. So tonight, at the end of the event, maybe you'll go home. You'll turn on the TV, you'll flip on Netflix, and the question you'll have to answer is, what movie, what show am I actually going to watch tonight? It's a difficult question. You could just say, well, I'll just watch whatever I watched yesterday. And that might be a good choice. Bake Off is a great show. But after 10 seasons of Bake Off, you might think that some of the culinary creations aren't quite as spectacular as you originally thought. So what can you do? Well, maybe I'll just broaden it. I won't watch the same show over and over again. I'll pick a genre that I'm particularly interested in. Scandinavian crime dramas. Highly recommended. A variety of shows. So you have a variety of things that you're going to be looking at. But I have to be honest, and I say this with great respect to my Scandinavian friends, after many seasons of this, it gets pretty depressing. So what else might I do? Well, I could just pick at random. I could pick any show at random from the Netflix catalog. And I guarantee that I'd look at something different every night. I guarantee that over time, I begin to sample all of the different shows that Netflix is streaming. But how many episodes of Guys with Kids would I have to sit through before I found something that I found interesting, that hidden gem? This is the same problem that astronomy faces, but maybe at a little larger scale. Every 30 seconds, there are 10,000 events coming from that telescope. Events that are detected using the software built by the University of Washington researchers. Every 30 seconds, you have to make a choice. Which objects are interesting? Which objects should I focus on? But 30 seconds later, I have another 10,000 events. And so what I have to decide now is, do I still watch this show? Do I still focus on this object? Or do I change my decision? 10,000 choices every 30 seconds. 10,000 decisions to make every 30 seconds. That is the challenge that we face with the flow of information coming from the Rubin Observatory. How do we address it? Well, we actually do what Netflix does. We use machine learning and we use AI, and we use that to predict what thing that you should watch, or what thing that you should observe or study in more detail. What is the next best choice? So what we do is we classify stars and galaxies. We classify them based on their properties, their brightness, their variability, how much their light changes as a function of time. And from this, we can determine which ones should we pay attention to now, like the supernova that we saw, that will change and fade away in just a few days, and which ones will just vary generally and just keep nurdling along, varying away like the RR Lyrae stars and the AGN that Mario talked about. And those maybe we don't have to look at today. Maybe those we can wait for a few weeks or a few months or a few years. And so we have to work out how do we classify at a scale that we've never done before. And the way that we do this is we bring together scientists with citizen scientists. Citizen scientists may be like you. Citizen scientists who can actually look at the data and look at the images and say, is this a star? Is it a galaxy? Is it an asteroid? Or in this case, is there evidence for activity from that asteroid, a cometary tail? The citizen scientists look at these images and label them and tell us what they are, and then we build models. And these models learn from these labeled data, and then they can work on the much larger sets that will come from Rubin. And now we use the power of AI to look for the tiny little features, the little tails that tell us that this asteroid is active. Activity that is due to the outgassing of volatiles and water from these active asteroids and comets. The water that, as Mario said, may have come from these comets as it seeded the planets and seeded our planet. By bringing together the power of AI with the data from Rubin, we can take the number of known active asteroids from a few tens to tens of thousands. And we can build on this to understand how water gets distributed within our solar system. But at the scale that we work at today, with a few thousand volunteers, a few thousand citizen scientists, there's no way that we can still work at the volume of data that's coming from the Rubin Observatory. So we build AI systems and we expand them so they don't need to work on labeled data. Even with all of the citizen scientists of the world, if you took 100,000 people, it would take them 100 days of work to just assign one label, one type of label, to all of the objects that Rubin will detect. So we expand our methods, we expand our techniques so they don't need to rely just on labels. So they can look at the data and recognize which objects are unusual. And from these objects that are unusual, we can separate out galaxies that may look like our own galaxy, the Milky Way, but at a much greater distance, or galaxies that are strange or anomalous. They're merging and distorting, and the gravitational interactions are distorting the shapes of these galaxies, stripping the gas, forming new stars. Galaxies that are extreme and unusual and anomalous, and it's often these unusual and anomalous objects are which give us the biggest tests of the theories for galaxy formation that we have today. Željko said that to get to this point has been a 25-year journey. Today, we use AI, we use language models to accelerate our discoveries. Language models like ChatGPT. We build AI that allows us to study the variability, the time series of data. We build new tools at UW to search for the signatures of a distant planet in the outskirts of our solar system. We even use AI to improve the image quality and the sharpness of the images that you see from Željko. but we also bring physics into our AI and the laws of the universe. And we do this because we need to know what the AI is telling us. We need to be able to explain the decisions that it's making. We have to understand the uncertainties on what its measurements and its predictions actually mean. We have to take a responsible approach to how we bring AI into accelerating the discoveries that we'll make from the Rubin Observatory. It's been a 25-year journey to get to this point, but in many ways, it's really just the start. Over those last 25 years, you've heard about the discoveries and the work that we've done. We've also lost our team members during that time, and we are deeply saddened at the fact that they can't get to witness the amazing aspects of the data that are going to come from the Rubin Observatory. Rubin's going to change the way we think about the universe. Rubin is going to do for astrophysics what the Human Genome Project did for understanding ourselves. By integrating AI with the data from Rubin, we can make the discoveries about how our universe evolves in the same way that we're understanding the structures of protein, or using AI to reveal and unravel the properties of our genetics. In 10 years' time, I hope that we'll be able to come back to show how we've managed to decode the universe using AI and our computational tools and the beautiful data that are coming from Rubin. But in many ways, this is just the start of the journey. 25 years ago, Nathan Myhrvold introduced Charles Simonyi and Bill Gates to a scrappy little startup called LSST, a scrappy little startup of academics whose idea was quite ridiculous, right? The idea that they could map out the sky. Today, we're taking the first steps in terms of understanding the science that we will get from Rubin. And in many ways, the way that we can actually do this is through the support that we get from the university and from the excitement that we find from the Pacific Northwest community, who understand that science and technology and brilliant students deliver on the promise of the Rubin Observatory, and that the University of Washington is in a unique place to deliver on that promise. So at the beginning I said that Rubin is a remarkable machine. And it is. But machines are designed and refined and built by people. Software is written and tested and debugged by people. Ideas and research come from people. AI accelerates our ability to make discoveries, but those discoveries are made by people. So I wanted to end by, and if we could just bring up the lights a little bit. I wanted to end by asking any of our Rubin team, can you bring up the lights? Can you bring up? Perfect, thank you. Whoa. So I wanted to end by asking those of you in the audience who are part of the Rubin team, whether you were involved in getting the university to take on this journey, whether you were building the telescope or writing the software that will undertake the science with Rubin. I'd just like, if you could just stand just for a moment. These are the people who delivered on a 25-year-old promise that took an idea that blossomed into this incredible observatory. These are the people, the University of Washington people, who built a telescope and observatory that is a fitting legacy to the power and the impact of Vera Rubin. And these are the University of Washington people who will deliver the science and make the discoveries that will change the way we think about our universe. So I think that is a fitting way to bring these talks to a conclusion. But I know from Jim that he said you might have a few questions. And so I think what we're going to do is we're going to open up the floor and have Mario and Željko come up. And then we'll take any questions you might have about this really fundamental change in the way that we're going to understand what our universe is telling us.
Thank you, Andy. Yes, as Andy said, we have an opportunity here for a few questions. We have a mic. I will run the mic. If you have a question, please come down sort of towards one of the wings or in the middle here, and I will run the mic. We have time for a few. Particularly if anybody's got a fun question about the universe. We have the universe's experts here, so this is your chance to ask them your questions.
Can we bring the light up a bit more?
Go ahead.
So the question I have is, we're looking at the southern sky. Is there plans for the future for another Rubin to see more of the sky?
Could you repeat, Jim, the question?
The question was about Rubin in the north. The question was about Rubin in the north. That's all southern sky. What about the rest of the sky?
At some point, there were some people advocating for it. One would initially think it will be much less expensive because it's copy number 2. In practice, it turns out it's not that large difference. It's maybe a factor of 2 to 3. And most of science you would get, you can already get from south. So the only strong argument is that you want a full sky map, but that doesn't bring you much more science. It would be nice to have it, but it's very hard to justify that expense when there are competing projects. There was a group of Russian oligarchs about 15 years ago who wanted to fund it and build it in Russia, but then they disappeared. We don't know what happened.
All right, we've got one over here.
Hi, this is very exciting. I was part of the transit detection team for LSST, and so it's just great to see everything that's going on. I was curious about how much progress, specifically for the missing satellites problem, that is, if we run cold dark matter simulations and try to predict how many of these satellite galaxies come into view, we're seeing less of them in reality. So how much progress would you say we'll make for that problem? And then secondly, I was quite interested in how you guys also develop the tools to be more accessible for people, for instance, making like this data as music, for example, for people who can't see. So sort of running through, in summary, what that process was like in designing those tools.
I'll take the first part of that, and then I'll pass it over to Željko to take the second part. We're only a week into the survey, right? We're not even a week into the survey. We're a few weeks into the commissioning that will get us towards the survey. So, what I can't say what we have discovered, but I can say that we will have one of the largest and most complete and most detailed maps of the satellites, both in terms of whether you're looking at satellites around our own galaxy or looking at the streams of galaxies throughout stars within our own galaxy, which one of our professors, Nora Shipp, is the world-leading expert in that, or looking at the satellites around nearby galaxies. So we will have a census of those at an unprecedented scale in terms of the depth and also the colors, so we can look at the properties of the stars within the satellites that we're detecting. And then the way to answer that is we have to couple it with the simulations and the models that the theorists that Željko was talking about. We are all observers. Our favorite thing is to annoy theorists by presenting data which is a challenge to different theories. But it's bringing together the simulations with the observations that we're going to get from Rubin that I think, and I said it's a 10-year survey, but the reality is within the first year we're going to make some incredible progress, not just in understanding the satellite problem, but also in understanding all of the near-field cosmology problems.
Thanks. I'll answer the question about using other methods to convey our data, like for example, music or sound. Thank you for reminding me of that. I failed to mention when I introduced Sky Viewer, the tool that you can get on your phone or your computer to look at that giant image that we introduced. You don't have just to look at it, you could listen to it. And Sky Viewer has a toggle. You can switch to music to sonified image where chimes and harps are used to tell you whether you are moving your cursor over galaxies or stars or clouds and so on. So if you have friends who would like to explore that aspect of Sky Viewer, please do let them know about it.
One more over here. Okay. This is a wonderful talk, of course. One of the things I'm really interested in is kind of like the genesis of the solar system. So things like, how did the terrestrial planets come to existence? You know, was it planetesimals or pebbles or anything else? So when we're looking at the solar system and its objects, what can that kind of tell us about the genesis of the solar system and how it was created?
Sorry, can you repeat that last word? What can we tell?
About the genesis of the solar system. What does the demographics tell us about it?
So this is what one of the most interesting things that we hope we'll answer. So here's an example. We know where the planets are today. And usually when you look at the solar system and you think about the solar system, you think, oh, this is what it's like, and it's always been like that, it's never changed. Well, guess what? Neptune is right now at 40 times more distant from the sun than the Earth is. When it was created, we think it actually was created about 2 times closer to the sun than it is right now, at about 20 what we call astronomical units. All the other planets in between were also much closer. Something happened 4.5 billion years ago to take those planets that were happily orbiting within 20 astronomical units from the sun and then expand them. And that expansion may have happened incredibly rapidly, on orders of tens of thousands of years, which is a blink of an eye in astronomy. We don't know the details of that process. What we miss are not theories, we miss data. So that's why I get so animated and excited when I start talking about 5 million objects or about 40,000 trans-Neptunian objects, because with all those objects, we'll be able to test all of those theories and hopefully throw all but one into the dustbin and know what's actually happened. So stay tuned, because in the next 3 to 4 years, we may have an answer for you.
All right, I'm afraid we'll have to cut it off there. We're astronomers, so we will stay up all night answering questions if you let us. I want to thank all of our speakers. I want to thank all of you for coming and spending time with us. This is truly the joy of our careers, to be able to share this with all of you. So thank you.
One last thing.
You have one more thing?
So before you all go, I just wanted to say one thing. There have been these incredible displays and talks throughout the whole of the country, in fact, the whole of the globe about Rubin. The largest number of attendees at any one of those events was 220 in Arizona. There are 600 people came tonight. So I just wanted to say, thank you, and you crushed it.
Thank you all. If you're a member of the Dirac team, please come up here and take a photo with us. And everybody, please get home safely. Thank you.